Hi there, my name is Declan Adams, and this is my final submission for Physics 1 of the Choose Your Own Adventure Lab. So to start, the purpose of my lab, so I chose to do the Slinky lab, was to examine the motion of a slinky dropped from static equilibrium, and then to compare the observed model to a predicted computational model to see if the slinky truly stayed stationary. And so before we cover that, there's some fundamental physics principles that we always should cover. So this lab focused very much on projectiles and specifically Newton's second law. So here where force equals mass times acceleration becomes really important because our forces of gravity and slinky rely on the y component being the mass times the acceleration due to gravity. And you can notice that gravity is in the negative direction and the slinky is in the positive direction. We'll mention why that's important in a second. So also from Newton's second law, we get concepts like the velocity update formula, which measures the change in velocity at two different time periods, and the position update formula, which measures position at two different time periods. And just to review the forces, we have gravity and the slinky, and then we also count for the force of drag. And so to briefly preview the results, did the bottom of the slinky truly stay stationary? Yes, and we'll discuss why in a second. So to look at our models, our system was the slinky plus the earth, so gravity, and our surroundings were nothing. And you can see on the right over here that they are going in two opposite directions on the y-axis, and those forces are equal and opposite in magnitude. And so for the experiment, the procedure was to first download the provided video of the slinky and upload it to Tracker, then using Tracker, find the slinky's position frame by frame to determine the observed position and velocity. Then using GlowScript, create a computational model that predicts what the position or velocity should be. Then finally to compare the observed and predicted models to determine if the slinky is truly stationary. And so with Tracker, you can see this video here on the right with all of the little red dots showing frame by frame motion of and position of where the bottom of that slinky is. And we're not really interested in this X one, we're more interested in this Y position. So you can see that it decreases after staying consistent for a couple of seconds. And here are our initial conditions. The mass of the slinky was 0.218 kilograms. The initial height was 1.75 meters. That's how tall this guy is here. I did have to randomly Google that. The initial position is shown here. Well, you see 9 here, but the initial position is here. And then the initial velocity is 0, 0, 0 because it started at rest. And so now for the code, the initial conditions that we just discussed are shown here as the mass, here's the position and the velocity, time is 0 because we're starting at 0, and then of course our magnitude of gravity is always 9.8, we have our j hat unit vector, and then a proportionality constant for the drag force, which was just a trial and error concept. And so here's our calculation loops, where this calculation loop is before the bottom of the slinky starts moving, so that's why time is 5.4 up here. And this calculates the net force acting on the slinky from both gravity and the slinky itself. And using the momentum principle, we're using the velocity update formula and the position update formula we discussed earlier. And the same exact process is done for up to 8.3 seconds when the video ends to see if it stays stationary and then starts to move. And so looking at our code output, we can see that for the first around 5.3 seconds, the Y position stayed stationary, and then as the slinky dropped, it went down on the position axis. Same thing with the velocity, that the velocity begins to change after 5.3 seconds. And so to model this in GlowScript, this is what that output looked like. And so to discuss these results, to compare our observed and predicted position models, we can see that they roughly follow the same trajectory. Of course, the observed had a little bit of experimental error just because it's hard to click frame by frame with exact precision, but they follow the same general trend. And so some sources of error, like I mentioned, were the center of mass. It may not have been correct for every frame. There was over 200 frames, so it was very difficult to have a very specific point for each. There was also some computational limitations because it doesn't have the full complexity of a real-world model, and it doesn't account for all forces like wind blowing on the slinky or it hitting the ground. And so for some conceptual questions, what does it mean and why does the slinky remain stationary at the bottom for a while? Well, this is because these two forces, as you can see, cancel out. So we have static equilibrium where there's zero velocity and no net force. And then what if we measured the top of the slinky instead of the bottom? Would it follow the same principle? No, because while it starts at rest in the first frame, it begins quickly moving after 0.04 seconds, so the position and velocity both update using our formula.